Hi Year 12, I'd like to post a quick video about a question from lesson 45. So lesson 45, question 2. There's a couple of things that do make it quite awkward. So the question is, in 2c part 1, you've got to find an expression for dy by dx for this equation here. So it's an implicit equation, so of course we've got to do things other than normal to find our dy dx. So x plus y over x minus y equaling 2y. This is the answer that we are aiming for. So a nice, relatively simple looking 1 minus 2y over 2x minus 4y minus 1. So I think we would just naturally kind of focus on that left hand side. It's a quotient, so I'm letting u equal x minus y and v equal the denominator x minus y. If I differentiate those, I'm going to have 1 plus dy dx and 1 minus dy dx. So that's fine, but then you put it in the quotient rule, it gets a little bit horrible, doesn't it? So the derivative of this, v times by du dx minus u times v dv dx all over v squared. If you expand that, there are a couple of things that simplify. So there's an x there and a negative x there that cancel. There's a negative y dy dx and a positive y dy dx double negative. They're going to cancel. So it does just leave you with those two adding to make 2x dy dx, those two combining to make a negative 2y. So that is my derivative of the left hand side. Of course, differentiate the right hand side, we've got 2 dy dx. So putting that all together, 2's cancel, but then after gathering terms, so I've multiplied up by that denominator there to give me that line. Then I have, well, I've put the y on that side, I've put this term on the left hand side, and then collecting those dy dx terms, I'm going to have an x minus y squared. And I could expand that bracket, but nothing's going to combine with that because I'll have an x squared, I'll have a minus 2xy and a y squared. Nothing's going to combine with that. So when I rearranged, I did that division, you can see I thought about it there, I've left it like that. However, unhelpfully, that looks nothing like the answer that has been given. So, you know, what have you done wrong? You've actually done nothing wrong, and I'll show you why shortly, but that is actually an equivalent answer. That is an absolutely fine answer for dy dx. It's just what you've done, you've made life more complicated for yourself by not thinking, right, what could I have done at the start to make that simpler? The horrible bit in that question is this purple bit here. It's doing that quotient rule and differentiating, having that implicit differentiation going on within that quotient rule. The way that the textbook wanted you to do it was to rewrite it first. So I know quotient rule in general is kind of quite awkward, particularly so with implicit, so we can easily avoid that. I can multiply up by that denominator there to leave me with x plus y is equal to 2y multiplied by x minus y. If I expand that bracket, so I could use product rule, but I don't need to, so don't. Expand that, and we're left with that, and now we can just differentiate each of those bits in turn. Differentiate x, we get 1, that's going to be dy dx. I've taken that 2 out, and then I've treated that like a product, so that'll be x dy dx plus y. Differentiate that, that'll be 4y dy dx. And now you can see I've got no squared terms, I've got no high powers at all. It's just a simple matter of expanding the bracket, collecting together the y dy dx terms, which I know you'll be happy with. And yeah, that is what was given in the question. So that obviously is how they were hoping that you would work that out. But what we've got to do now is somehow kind of reconcile these two answers, so that one and that one being the same. And it comes from this. Normally, when you've got an equation written as y equals, there's just one way to write it. There's one way to express it as y equals, so we always have dy dx coming from that one equation. But thinking about this, there are a number of ways we could have written that equation. Well, here we multiplied and we wrote it without the fraction. In exactly the same way, there's a number of ways of rewriting the original equation. There's a number of ways that you can write dy dx, and one thing that we could do kind of very simply, okay, I've got an expression for 2y there, so I could just rewrite y as x plus y over 2 lots of x minus y, and then I can substitute that expression for y into there, and it's going to get me an alternative dy dx. Alternatively, I could have just taken this x plus y and this x minus y and put that in there. There's essentially an infinite number of ways of expressing this dy dx. So I've had a little look. I don't think there's an easy way to get from one to the other. However, you can justify it quite nicely by picking a point. If I pick a point when y is equal to 1, and I'm going to use my original equation to work out what the x value is, so I'm going to have a point on the curve. So I will have x plus 1 over x minus 1 equaling 2 times y, so 2 times 1. So now I've got an equation I can solve. I know that x plus 1 is equal to 2 lots of, multiply it by that x minus 1. X plus 1 is 2x minus 2. And we can see there, all right, x is equal to 3. So I know that the point 3, 1 is a point on this curve. So if I take my two alternative forms of dy dx, so at the point 3, 1, the gradient dy dx using this more awkward expression is equal to y, which is 1, over 3 minus x minus y squared, so that will be 3 minus 1 squared. That will give me 1 over, that bracket is going to be 2 squared, that's going to be 4, 3 minus 4, negative 1, so the gradient is negative 1. If I use this expression here, so the answer that was given in the back of the book, and again work out that expression at 3, 1, I will have 1 take away 2 times by 1, so that's going to be 1 minus 2. So this is my expression, sorry, for dy dx. And then on the denominator, I'm going to have 2x, that'll be 6, minus 4, minus 1. So I'll have a negative 1 on the top, and I will have 6 minus 4, that'll be a 1 on the bottom. Again, giving me that same answer. Okay, so hopefully that's enough to kind of justify that it is the same expression. It's just that that is a more complicated expression. The answer in the back of the book only give this solution, but of course, if this was an exam question, they would take both of those options. Alternatively, they might steer you in such a way that there's only one sensible solution. But if you got that, well done. You've done some really tricky differentiation, trying to sort out what that quotient rule is doing particularly. And this is part 2. So part 2, again, I did it the given way using the quotient rule. You get quite a complicated equation involving powers. However, just look, there's a 1 there. This question is designed for you to take that denominator and multiply it on the right-hand side. You end up with a really simple expression. So I would say that this one definitely you should have spotted before. The other one, arguably you still ended up with a product. It was a little bit awkward, but here that's so much easier to differentiate. 2y dy dx is equal to x dy dx plus y. The one, of course, vanishes. And just a couple of steps easily takes you to this. And then just a little note I put at the bottom, leaving it, we'll get the same answer, but then I change. It's not really the same, is it? It's not the same equation, but it's an equivalent expression. Okay. What we're saying, of course, is that the two dy dx's are equivalent for any point on that curve. Okay, I hope that clarifies things a little for you.